Department of Electrical Engineering, National Institute of Technology, Rourkela. The speaker of the present session is Dr. Banibrata Mukherjee. Now let me introduce Dr. Banibrata Mukherjee to you all. Dr. Banibrata Mukherjee received his BE degree in Instrumentation and Electronics Engineering from Jadavpur University, Kolkata in 2009 and subsequently MTech degree in Instrumentation and PhD degree in Electrical Engineering from IIT Kharagpur in 2011 and 2016 respectively. Currently, he has been serving as an assistant professor at Advanced Technology Development Center at IIT Kharagpur since June 2019. Prior to joining IIT Kharagpur, he worked as an assistant professor in the Department of Electronics and Communication Engineering at NIT Rourkela for around 3 years. He has been the recipient of Early Career Research Award from SCRB in 2017 and winner of hackathon conducted by the CENSC IISc Bangalore in 2022. He is a senior member of IEEE and also editorial board member of prestigious journal Scientific Reports from Nature portfolio. His current research areas primarily include vibration energy harvesting, self-powered system development, interfacing power management circuits, sensor fusion, navigating system, robotics, MEMS, and embedded systems. He has been executing several sponsored projects and published many peer-reviewed journals and conference papers in these research areas. With this introduction, I introduce Sir Dr. Banibrata Mukherjee sir to address the participants. Over to you, sir.
Yeah, thank you for your introduction. Yeah, just a minute. Yeah, so hopefully you can see my screen. Can you see the screen?
Sir, yes, sir. It is visible.
Okay, and hopefully I am audible as well.
Yes, sir. Please make it. The screen is not visible now. You are visible. Yes, sir. Please make it full screen, sir.
Yeah, so I
Yes,
hope
sir.
you can see my screen and I am audible clearly,
Yes, sir.
right?
Yes, sir. Yes, sir.
Okay, so thank you for your nice introduction. Of course, thanks to Professor Arnav Ghosh for organizing this particular event and inviting me as a resource person. So it is my privilege to deliver my research areas to this forum. And of course, the specialty is this is my that earlier organizations where I was associated for 3 years before joining IIT Kharagpur. Yeah. So let
Thank
us
you, sir.
start. Yeah. So let us start the session. So today, as you can see, the topic what I have chosen is the development of vibration and solar energy harvester based cell pod sensor system and its application towards AI/ML enabled structural health monitoring. And so most of you are aware of that right now this energy is one of the most emerging area of research, specifically the renewable energy, and it has wide application in various domains. So specifically in this lecture, we will be focusing on the vibration and solar as the renewable energy sources, using which we will be extracting the electrical energy and we will be using them to store and power up some low power devices, sensor nodes, IoT nodes to make the cell pod sensor system. And finally, we will demonstrate that some research aspects where we can find its application towards the futuristic AI/ML enabled structural health monitoring. With this introduction, let us discuss about the content in little more detail. So specifically, we can see the three broad aspects are there. Firstly, I will discuss about the basic background related to the vibration and solar energy harvesting technology and its applications to create a platform and background for all the participants, because we can understand that you are having the diverse background and mixed audience having different kind of backgrounds with different specializations and this different levels as well. So that's why, to make parity, first to create the background, we will discuss the basic concepts and preliminary ideas about this particular topic, where we will discuss about the energy harvesting concept, its applications, benefits, and focus on the vibration and solar energy harvesting aspects, including the various transduction mechanisms and interfacing circuits. After that, I will discuss and focus on our ongoing research activities in this particular directions for energy harvester, along with its application to develop cell pod sensor system, where we will show you the developed energy harvesters along with its interfacing power management circuit. Also, the hybrid energy harvesting concepts we will talk about, and then we will demonstrate the cell pod sensor system applications. After this, finally, we will show the application demonstration towards AI ML enabled structural health monitoring. Okay, so I hope the content or the flow which I am going to cover in this particular session is clear to all of you. And I request all of you that at any point of time, if you have any kind of specific doubts or any clarifications required, please feel free to stop me and clarify your doubts. Okay, so with this, let us proceed. We are aware that in today's world, various embedded systems, including the portable electronics, gadgets, wireless sensor networks, medical devices, they have become indispensable in our day-to-day life, right? But in order to make these devices work, we require the battery, because these devices relies on the conventional uses of batteries to meet their power requirement. Is not it? At the same time, we know that the conventional battery, they are having couple of issues and challenges. For example, battery is having limited lifetime. As a result, in regular interval, we need to replace it. Now, once the battery dies down, we need to dispose it, and because of its disposable, pollutions will be caused, because we know that battery is the made of different chemical composition materials. If we throw them away without any kind of processing, it will cause pollution. Another thing is that sometimes in some critical applications, it is often impractical to replace those batteries. For example, the implantable medical devices, wireless sensor nodes, where it is inconvenient and the locations are inaccessible. In those kind of applications, it is sometimes impractical to go in that respective place at regular intervals and replace the batteries. So naturally, the questions will come, what will be the alternative better solution? To address these limitations of the conventional battery, the energy harvesting is coming into the picture. What do we mean by energy harvesting? It is nothing but the conversion of ambient energy, which is present in the environment, into electrical energy. And of course, we will be processing that energy through dedicated interfacing power management circuit. Then we will store them in some that rechargeable batteries, or specifically some supercapacitors, so that we can use that energy to power up some devices, our daily uses devices, low power electronics nodes, sensor nodes, IoT gadgets, and so on. Isn't it? So eventually, the energy harvesting is converting the ambient energy. What are the ambient energy present? For example, the non-conventional renewable energy sources we can consider as the solar as one of the most important ambient energy available. Then we can think of about the vibration, which is also ubiquitously available in different areas. Further, we have the wind energy, heat energy, radio frequency wave energy, and so on. Where we can find its major applications: in wireless sensor networks, in medical equipments like for powering the pacemakers, for powering remote infrastructures. We can consider its application in self-charging consumer electronics, where using the available ambient energy by storing them, we can use it for charging different consumer electronic devices. In smart city applications, to make use of these renewable energy sources for meeting the power requirement of our household appliances and different gadgets, we can think of its applications. Followed by that, also we can think of its application in the domain of structural health monitoring. Okay. So this is the generic background about the energy harvesting technology. Why is it required? What is its background? What are its applications? And what are the dominant energy sources which are available in the ambient, which we can extract to convert it into electrical energy, process it, and use it to power up some low power devices or sensor nodes. Right? So I hope the background is clear to all. Now let us see some practical example of wireless sensor networks or wireless sensor nodes for structural health monitoring. Like let us consider, suppose this is, you can consider some railway track. You can consider this particular railway track is suppose going through some tunnel. Okay. Now through this tunnel, that tunnel can be 100 meters or 200 meters long, depending on that locations. So we are how to know that what is the exact health conditions of these railway tracks as well as the tunnel in which it is present. So typically what we can do to monitor its health, we can install a couple of sensor nodes over here. What kind of sensor nodes we can think of? Like temperature sensors, like strain sensor or stress sensor, pressure sensor, force sensor, vibration sensor. These are the kind of sensors we can install in the track as well as in the tunnel, which can continuously monitor the different vibrations, stress, temperature, those kind of parameters. And by monitoring those parameters, we can extract some other quantities like resonant frequency as well. And from there, we can have some idea that what is the conditions of the tunnel as well as the railway track, right? Because manually it is not convenient that you will go to that place and put some sensor nodes and take that reading and then come back to your control room and do the processing. That is quite impractical and inconvenient, is not it? So that's why we can install that different kind of sensor nodes which will continuously monitor those important parameters, and those parameters we can transmit wirelessly to the base stations, and from there we can transmit it to the server, which the human being or the user can access, and also those data can be stored in some databases so that later on also we can access them, and from there we can analyze all the informations of the sensors, based on which we can get the clear-cut idea about the health conditions of the railway tracks or the bridge or the tunnels. So in these kind of applications, that now, of course, the sensors which we'll be using over there, they will depend or rely on the conventional uses of battery to meet their power requirement and to make them work. Now, of course, as the battery is having limited lifetime, so at certain specific time interval, the battery needs to be replaced, is not it? But that is also not a convenient option that at regular interval we will enter into the tunnel and go to the railway track and replace the battery and do our job, is not it? So that's why in these kind of applications, if we can think of that whatever the energy present or available in the ambience of the tunnel or the railway track, like vibration energy or heat energy or solar energy, whatever is available. Because of course that if the tunnel is very dense tunnel, we cannot think that solar energy can enter there. But the other kind of energy, and depending on the locations, we can think of the whatever energy available, renewable energy sources. It can be vibrations, it can be thermal, whatever. So by some means, if we can convert those ambient available energy into electrical energy and process them, store them in the dedicated power management circuits and use them to meet the power requirement of the sensor nodes, that is good enough, and that is very much convenient and effective for this kind of application and the scenarios, is not it? So here in these scenarios, what we can consider as the basic component of the energy harvesting unit, which we can install in the vicinity of those sensor nodes. And you can understand the sensor nodes, typically the kind of sensors which we generally use here. They are typically very low power sensor nodes or the IoT nodes, which typically can take in the range of microwatt to milliwatt kind of power to make them work, right? So it is of course not with these kind of applications we are mainly considering or focusing with respect to the low power sensor node devices, and for which we can develop or install the corresponding energy harvesting unit to harvest the ambient available energy, store them, and use it to meet the power requirements of this kind of sensor. Now, if we look at the basic components of the energy harvesting unit, what we can think of course, the first element will be the mechanical energy harvesting structure, which is the basic transducers we can consider, or the sensing element, which will directly come in contact with the ambient energy and convert that ambient energy into electrical energy. Then that energy that process it through the dedicated energy or power management interfacing circuit. Then we can store that energy in some supercapacitor with high value. And finally, using that energy, we will be able to drive the sensor nodes or the microcontroller or the peripheral devices. So these are the typical components which can be present in the energy harvesting unit, which we will be developing, which we will be discussing or focusing in detail, so that whole unit we can install in the vicinity of these tunnels or the railway tracks to generate the corresponding electricity energy from the available ambient energy and use it to meet the power requirement of the sensor nodes. Okay. So let us proceed further to see what are the dominant energy sources. The first dominant energy sources can be vibrations, which you can find in different structures, different machineries, wind, ocean waves, and so on. The next source of energy you can think of as the solar. So this is just the typical vibration energy. Suppose this is the vibration energy and this is the vibration energy transducer, which convert the vibration energy into electrical energy. What are the transducers we will be discussing after a few minutes. Then we can think of the solar energy. So basically, we can think of the solar cell or the photovoltaic cell, which can convert the solar energy into electrical energy. Then we can consider the thermal energy. We can think of the Seebeck effect, Peltier effect based devices, which can convert the heat energy into electrical energy. Further, we can consider as the radio frequency energy as another ambient energy sources. So which are abundantly available, right, in different kind of in form of electromagnetic waves, which can be basically coming because of you have this satellite communications, TVs, radios, mobile phones, and so on. So these are some of the very widely used or widely available renewable energy sources. So out of them, in this lecture, we will be primarily focusing on the first two, that is the vibration and solar, along with the corresponding energy harvester and power management circuit. So specifically, if we talk about the vibration energy harvestings, that is widely available sources. Where we can find the vibration energy? We can find the vibration energy from vibration of different heavy machineries, different electrical equipments, motors, washing machines, car engines, bridge, washing machine, HVAC vents in your building, wind, ocean wave, and so on, which are the sources of vibration energy. Is not it? What is the typical vibration available in these kind of basically elements or this kind of environment? Typically, you can consider the vibration amplitude in the range of 0.1 meter per second square to 20 meter per second square, and the frequency range can be within 200 hertz, less than 200 hertz typically. Okay. Now, if we specifically focus on the popular transduction mechanism for converting the vibration energy into electrical energy, we can consider as piezoelectric is one of the most widely used transduction mechanisms. So you can see that here, if we consider this is one cantilever and this is the piezoelectric material placed over this particular cantilever. And when this cantilever is subjected to vibration, then what will happen? The piezoelectric which is attached to the beams or the cantilever, they will be also subjected to vibrations. And as soon as the piezoelectric will be exposed to the vibrations, it will produce electricity or charge accumulations will be there across its electrodes. And because of that, we can expect the output voltage from the piezoelectric devices. Is not it? So in this way, the piezoelectric is one of the most popular transduction mechanism to convert the vibration energy into electrical energy. Next popular transduction mechanism is the electromagnetic energy, which works based on the Faraday's law of electromagnetic induction. Here, what we can see, you can consider some frame, typical frame, where you can have this mass spring arrangement is there, and a coil is wrapped around this mass, and at the bottom of this frame, we have some permanent magnet. So when this whole assembly or the structure is subjected to vibration, we can easily see that there will be relative displacement between this mass spring coil assembly and the magnet. Because of that, the varying magnetic field will be created. And because of that, we can expect the induced EMF across the coil based on Faraday's law of electromagnetic induction. Isn't it? So this is the transduction mechanisms or the concept which we can extract to convert the vibration energy into electrical energy using this kind of electromagnetic transduction mechanism. Another kind of transduction mechanism we have that is called as the triboelectric transduction mechanism. In this case, we have two different materials are required. You can see this blue one correspond to the electropositive material, so which is basically that, and another material is there which you can see which is holding the negative charge, and this one is holding the positive charge. So when these two materials will come in contact to each other, so one is basically so one is prone to accept electron, another is prone to reject electron. So that's why one is electropositive, another is electronegative kind of material. So when they will come in contact to each other, there will be charge redistribution. And again, if we just continuously apply the vibrations and continuously they are contacting and separating, conducting and separating, if this phenomenon happens, so then what we can see across the electrodes, here the top yellow that and bottom yellow, they correspond to the electrode. Across those electrodes, we can expect the voltage or EMF generated across the electrodes. In this way, this triboelectric device converts the vibration energy into electrical energy. So these are the three popular transduction mechanisms which can be used to convert the vibration energy into electrical energy. And all these three type of energy harvesting transducer or structures we have developed and we have worked on. So later on, in the research, when we will discuss about that research aspects and our developed devices, so then we will demonstrate them. Okay, so right now we are creating the background about the technology. Okay, I hope till now it is clear to all. Now, just the three transduction mechanisms what we have talked about, let us discuss a little bit more elaborately one by one. So first is the piezoelectric transductions, where we can see that piezoelectric is having two kind of effect. One is called direct effect. That means if the vibration is applied to the piezoelectric device, it will produce electricity. It will also exhibit the reverse effect. That means if the alternative current or AC voltage is applied across the piezoelectric material, then it can produce vibration. But for this vibration energy harvesting purpose, we use the direct effect so that the piezoelectric can convert the available vibration energy into electrical energy. It can have two type of configuration. One is called as the unimorph, another is called as the bimorph. So unimorph means you can see this red one correspond to the structural layer that you can think of as the steel or silicon kind of structural cantilever material, on top of which we have deposited the piezoelectric material. And of course, across the piezoelectric materials, we should have the electrode across which the electricity or EMF we can measure, and we can basically that EMF will be developed, which we can measure. Right. So if the piezoelectric material is deposited in one side of the structural layer, we can consider it as the unimorph structure. And if the piezoelectric layer is deposited in either side or both sides, so then we can consider it as the bimorph configuration. What are the commonly used material? We can consider lead zirconate, titanate, PVDF polymer, aluminum nitride, zinc oxide. These are the kind of materials which exhibits the piezoelectricity property, which we can use to develop the piezoelectric based transducers for converting the vibration energy into electrical energy. And from here, we can see that if it is exposed to vibrations, we can see the voltage is produced across the electrode of the piezoelectric layer. Right. So this is about the piezoelectric transduction mechanism. Next one is the electromagnetic transductions. So here, as you can see, this is mass spring assembly, where you can see this is the whole frame. And here you have this spring, this is the mass, and a coil, pickup coil is wrapped around this mass. And in the bottom of this frame, we can have the permanent magnet. So whenever this whole frame is subjected to the vibrations, which can come from the ambient, right, like some bridge, machines, those kind of equipments or the devices or the environments, then there will be, of course, the relative displacement between this mass spring system and the magnet, because of which the varying magnetic field will be created, which will in turn generate the EMF across this coil. And in this way, this particular assembly can be used to convert the vibration energy into electrical energy. Isn't it? So this works based on the Faraday's law. Now, another transduction mechanism is the triboelectric transductions, which works based on the coupled effect of contact electrification and electrostatic induction. What we can see, as I mentioned a few minutes back, that triboelectric transduction, it works based on the two different materials having different electron affinities. So you can see this blue one is one material, this ash color is another material, material 1 and material 2. The material we should choose in such a way that one should be prone to accept electron, another should be prone to reject electron. So that is, one is kind of electropositive, another is kind of electronegative material, so that when they will come in contact to each other, the charge redistributions will be there, and we have deposited that metal electrodes on top of this upper material as well as the bottom of the lower material, so that across the electrodes we can expect the voltage produced across them, right? So now when I firstly press it, then you can see this is plus positive, this material is that positive, this is negative. They will come in contact and charge redistributions will be there. At that particular time, we can see no EMF is produced across the electrodes. But as soon as you separate them out, then what will happen? The charge redistributions is happening, and towards the electrode, the charge will be transferred, so that across these two electrodes, I can get the voltage produced or EMF produced across these two electrodes, right? Now, of course, at free of cost, we cannot get anything. So if you think that you just press one time and then it will continuously give you the electricity or voltage EMF produced across that, absolutely no. As long as the vibration is there, it will convert that vibration energy into electrical energy, because at free of cost, it cannot give anything. So that's why you can see that if you keep it at these positions for longer time, then after a certain amount of time, again, you can see the null deflection. That means no voltage is there further. Then after that, if you just press them again and again release them, so in this way, if you just continuously press and release, then only you can get the continuous voltage output across the electrodes. And in this way, it can convert the vibration energy into electrical energy, right? So whatever I have explained through this diagram, so that is written in this text, right? So I hope till this point, the three type of primary transduction mechanism, that is piezoelectric, electromagnetic, and triboelectric, are clear to all of you, which are used to convert the ambient vibration energy into electrical energy. Isn't it? So now let us proceed further. So what kind of materials we can think of? They are very easily and available household materials like simple paper, Teflon tape, silk, wool, nylon, PVDF polymer, PDMS polymer. Simply household available materials can be used to develop this kind of triboelectric transducer based energy harvester. Okay. So moving forward, next let us see the solar energy harvesting aspect. So of course, the vibrations we have talked about and three type of transduction mechanisms we have discussed. Now we'll move forward to the solar energy harvesting. Of course, for the solar energy harvesting, we can use the simple photovoltaic cell or solar cell for this purpose. As you know, the solar energy is the significant source of power and energy or energy. However, this particular energy is periodic, isn't it? Because only when the sunlight is available, we can get the maximum output from this. In case of cloudy weather or night time, the intensity is significantly reduced or no intensity is there. In that case, the output will be significantly affected. So that's why this is typically periodic, intermittent, and affected by intensity and wavelength of light. So what this photovoltaic cell or the solar cell typically do? So they consist of the PN junction. On this PN junction, when the photon will be incident, so it will induce the electron hole pair. That electron hole pair generations will be induced, and this will in turn produces the current. Right? So you can see this is the typical solar cell on which when the photon is impinging on the solar cell or the sunlight is incident on that. So then here as it consists of the PN junctions, and you can see this electron hole pair generation is happening, because of which across the electrodes we can expect the current, because of which you can see this light is glowing. So this is about the solar energy and the solar cell, which is used to convert the solar energy into electrical energy. Now, one point to remember in this particular sessions, primarily we are talking about its application, the applications of the energy harvesters in basically developing cell pod sensor systems, which are typically which will consume low power in the sense of some MEMS sensors you can consider, or miniaturized devices, or low power electronic gadgets, or sensor nodes, or IoT nodes, which typically consume the power in the range of microwatt to milliwatt. Okay, so for that purpose, even if we can use the photovoltaic cell or solar cell, but we do not require very high rating solar cells. Even a few watt solar cell rating is sufficient for the applications which we are targeting or which we are going to discuss. Okay, I hope till this point it is clear to all of you. Okay, if it is fine, let us proceed further to see some applications. So we can see enormous uses of the applications of the energy harvestings for health monitoring purpose, wearable electronics, self-powered devices, smart houses, wireless sensor network, implantable sensor, industry 4.0, and so on. So we can see different applications, like you can consider this person, suppose some sportsman. So if we want to monitor the health parameters or different that physiological variables parameters like heart rate, temperature, sweating, so those kind of parameters, then we can install some sensor nodes in the body of the sportsman or the athletes. Right now, in order to power up those sensor nodes, you need some battery. So in this case, what we will be doing, instead of using the battery or the conventional power supply, what we can think of, we can install some vibration energy harvesters in the body or the vicinity of the sensor nodes. And whenever the persons will be jogging or walking or running, then because of the body vibrations, those energy harvesters will that produce the electricity energy, which will be processed further through its dedicated power management circuits, and that can be used to power up the sensor nodes which are installed in the athletes or sportsmen's persons, which will help you to monitor different physiological parameters. Is not it? Like again, here you can see that in this particular, for this particular persons, here we can see that some smartphone is wrapped around the wrist, and it will also include couple of sensors to measure the sweating aspects, perspirations, then the calorie generations, or smartwatch for monitoring the different physiological activity. So in order to power them, we can use the energy harvesters, we can install them, and those energy harvesters can that produce that convert the vibration energy into electricity and use it to power up the devices. Even we can consider some, there is some that biochemical kind of sensors are also there, which can convert the different kind of chemical energy. For example, because of the sweating, that the energy, so whatever the chemicals will be released, so from that also they will be that help you. So kind of the biofuel cell you can consider. Those biofuel cell, they can convert the that because of the sweating, the chemical energy what is produced, that can be converted into electricity to meet the power requirement of your different devices. Then we can consider the smart house. So on the rooftop of the smart house, we can consider, we can install the solar cell, we can install the piezoelectricity or the triboelectric or electromagnetic kind of devices or energy harvesters, which can combiningly convert. There can be solar cell which can convert the solar energy into electrical energy. There can be the different that vibration energy transducer like piezoelectric, triboelectric, electromagnetic, which can convert the that wind energy into electrical energy, and all the energy we can that store in the supercapacitor and use it to meet the power requirement of low power electronic devices or gadgets or the appliances. Is not it? Further, we can consider some self-powered tire pressure monitoring system. Like you know that in the vehicles, if we want to monitor the tire pressures, we need to mount the pressure sensor, right? And now, if we think that for pressure sensors, we will not be using any dedicated power supply or battery. Rather, what we can do, in the vicinity of those power that pressure sensors, we can install the vibration energy harvesters, which will produce electricity energy from the that car vibrations during running, and that energy can be used to meet the power requirement of those pressure sensors. So here you can see that typically tire pressure monitoring sensor is there. And here we can consider the rechargeable battery or the supercapacitors. So what we can consider here, we can consider some that ambient energy harvesters will be installed there, that will convert the available energy into electricity and store it in rechargeable battery or supercapacitor and use it to meet the power requirement of the sensor nodes to develop the kind of self-powered tire pressure monitoring sensor system. Right? So this is just to give you the idea about the practical and beautiful applications of these energy harvesting concepts for developing the cell pod sensor system, which are widely used in enormous application in our day-to-day life. Right? I hope till now it is clear to all. If it is clear, let us proceed further to see some of the interfacing electronics aspects for our vibration energy harvester. Okay, so till now we have mainly discussed about the transduction mechanisms, right? And the kind of harvesting structure. So basically the structural point of view we have discussed, or the transducers we have discussed, and also we have seen their beautiful applications to it. Now, suppose for example, the vibration energy, if we talk about the vibration energy, it will be converted into electricity, and the electrical energy which we will get as the raw output, that will be also kind of the, if I consider some sinusoidal vibration is applied, the AC output will be also I can consider as the sinusoidal AC output in terms of voltage or current, is not it? So eventually the AC vibration correspond to AC voltage or AC current. Now, you know that typically to meet the power requirement of low power sensor nodes or the devices, we require some DC voltage like 3.3 volt, 5 volt. These are the kind of voltage which is required to power up the sensor nodes or the IoT nodes, isn't it? And of course, the corresponding DC current will be also there in the range of microampere to milliampere. So typically, the requirement is in terms of DC. So of course, we can understand that the very basic building block or the interfacing electronic circuit which we need between the energy harvesting structure and the load, sensor load or the IoT nodes, that is the some AC to DC rectifier circuit, is not it? Which will convert the AC signal into DC signal. Now that is the basic fundamental requirement. So we will start from there, and gradually we will see the challenges and the innovations required in the research aspects. And then we will discuss about the research flavors and the research directions as well in this particular field. As I mentioned, the ambient energy is converted into electricity using the harvesting structure like piezoelectric, triboelectric, electromagnetic, solar cell, etc. Then I need to connect that output or feed that output to the dedicated interfacing circuit. And then that circuit output, we need to store it using some supercapacitor, for example. And also we require some voltage regulation, because in order to drive the load electronics like some sensors or some IoT nodes, we need a dedicated that constant power supply depending on the dataset requirement like 3.3 volt or 5 volt DC, right? So we need the voltage regulator, we need the storage device, and in the interfacing circuit also we need the AC to DC rectifier circuit along with the filter and other kind of accessory circuits, so that I can convert the available vibration energy into electricity energy properly and use them to meet the power requirement of different low power devices, right? So as I mentioned, that the first requirement, if I consider the piezoelectric or triboelectric energy harvesting structure, which are exposed to the vibration energy and gives the AC voltage or AC current as the immediate output, right? So then I need a simple rectifier circuit, for example, a bridge rectifier, if we consider, in order to convert that AC signal into DC signal. Then we require some smoothing capacitor or this RC filter, so that I can convert that pulsed DC into, so that rectified output into the kind of pulsed DC, and further smoothen it to get that almost kind of DC with less ripple, so that I can use that voltage or the energy to power up the DC loads or the low power electronic devices or sensor nodes or the IoT nodes, isn't it? So that is the very fundamental and basic requirement. But we will now discuss that if I use this simple bridge rectifier, then what kind of challenges are there, for which we need to think of the innovative circuit strategy or the innovative interfacing circuit scheme for avoiding those kind of challenges and design or develop a stable and efficient and beautiful energy harvesting structures, including both the energy harvesting structure as well as the interfacing circuits, along with the that rechargeable, that storage device or as well. Okay. Now suppose here we can consider the some piezoelectric or triboelectric device. What we can consider, the equivalent electrical equivalent circuit of the piezoelectric and triboelectric can be considered as one resistor and one capacitor in parallel. So the electrical equivalent circuit of piezoelectric and triboelectric can consider as the current source in parallel with resistance and capacitance. That is the typical electrical equivalent circuit of any piezoelectric or triboelectric device. Okay. So when you are applying the vibration, then what will happen? The current source, it is acting as the current source. So current will be produced, AC current will be produced. Now that AC current, when it will be multiplied by its impedance, impedance means what in this case? That R and C parallel combination, then you will get the corresponding voltage. Is not it? Now if you plot the current and voltage in a same graph, then what you can see? You can see that since they are acting as the current, basically that current sources, so you can consider this blue line correspond to the current, AC current, which is resulting because of the applied vibration. Now that current, when it is multiplied by the impedance of these piezoelectric or triboelectric harvesters, what is the impedance? R and C parallel equivalent. So then I will get the corresponding output voltage, which is depicted by this green waveform. Eventually, you can expect, since its impedance consists of one resistance and one capacitance, typically I can surely expect the phase difference between the current and voltage. Is not it? So you can consider that if this is the typical current, then this green one will be the corresponding voltage expression or waveform, and there must be the phase difference between this current and voltage waveform depending on the values of R and C. Now if you plot the instantaneous power, this current multiplied by voltage, then you can see here there will be in the power waveforms, you can see some negative part and some positive part. When the negative will be there, you can see till this point, till this particular point, your current is positive but voltage is negative. So till this point, this power, effective power, is becoming negative. On the other hand, from this particular point up to this point, both the current and voltage are positive. So eventually the power waveform is also positive. Again, up from here to here, your current is negative and voltage is positive. Then also I am getting the power as negative, and likewise it will go on. So eventually from this waveform, what we can see, there is a positive in the power waveforms. There is one positive part and one small amount of negative part. So eventually what we can depict, or what we can observe from here, that in the overall power waveforms, so there is some positive part and some negative part. As a result, the resultant power will be reduced because of the negative power effect. Now practically, what do we mean by this positive power, negative power? Since this is a transducer, its job is to convert the vibration energy into electrical energy. So basically you can consider the mechanical energy into electrical energy conversion is happening. So positive power means you can consider the mechanical energy is converted into electrical energy, but negative power you can equivalently consider it as the electrical energy is converted into mechanical power. So energy return phenomenon you can consider. That is the physical interpretation of the negative power. So eventually what I want to highlight over here is that if I use a simple bridge rectifier circuit for as an basic interfacing element for this vibration energy harvesters for piezoelectric or triboelectric, then I will not get the efficient power extracted output. Why? Because of this phase difference, there will be some negative power. As a result, the overall power will be getting reduced. So what we can do, or what kind of scheme we can come up with in order to reduce or eliminate the negative power, that is giving the one kind of beautiful research direction, right? So in these orientations, people have worked on different kind of circuit scheme or strategies to take care about this effect. Here again, just the LT spice simulation result is shown to give you that more practical idea. So here we consider that this is the typical equivalent circuit of the piezoelectric transducers, current source in parallel your capacitance and resistance. This is the bridge rectifier circuit, and this is the smoothing capacitor or the RC filter across which we are getting the rectified output. So you can see that this is the typical, that blue one is the current, green one is the voltage, and we can plot the instantaneous power where you can see both the positive and negative power to give you the practical, realistic, simulated idea. Okay, the corresponding experimental validations also we have done. So this is to give you the simulations from how it is happening. So this particular standard bridge rectifier circuit, of course, it is simple, it is reliable. But what is the most important limitation? The limitation is the energy conversion efficiency is degrading because of this negative phenomenon or energy return phenomenon. In order to avoid this phenomenon, what we can think of, we can come up with the synchronous switch harvesting on inductor kind of one. That beautiful circuit topology is there, using which we can eliminate the negative energy part. How we can do that? You can see this is SSHI circuit. So it is simply SSHI circuit comprises of an inductor in series with a switch. You can see that earlier we have the piezoelectric or triboelectric device whose equivalent circuit is our this current source in parallel R and C, and that was connected directly to the bridge rectifier and the RC filter or the smoothing capacitor or smoothing filter. In between, what now we are incorporating? One switch and one inductor. Okay, what will be its job? Its job is, why we want to use it? We want to use it to eliminate the negative power from the waveform. Fine, that is our objective. How it will do that? How we can achieve this that always positive power? Suppose in order to achieve always positive power, my voltage and current should be either both should be in a particular instant, either both should be positive or both should be negative. How we can do that? Suppose from this point here you can see the current is over here. So this is the current waveform and this is the voltage waveform. Now here is the zero crossing of the current. When the current is zero crossing from negative to positive, the voltage is still in the negative, because of which we are getting the negative. So using this SSHI circuit, what we will be trying to do is essentially that whenever the current zero crossing is there, then and there the voltage I want to flip from negative to positive. Now suppose the voltage is negative. So when the zero crossing is happening, in order to eliminate the negative power, what I can do at this particular instant, I want to flip that voltage from negative to positive, so that in the entire directions, entire duration in the positive half of the current, the voltage will be also positive. So that both are positive, then output power will be positive, instantaneous. Similarly, for the negative side also, when the current zero crossing is there, you can see at this particular point, the current zero crossing from positive to negative. At this particular point, I will be flipping the voltage from positive to negative, so that both current and voltage will be negative and power will be positive. So that I want to achieve through this simple scheme. So what essentially we will be doing? We will be detecting that zero crossing of the current, and zero crossing of the current correspond to the peak displacement, right? So that is basically, your this I current is your I equals to dq dt. If the charge generation is q, so I will be your dq dt, right? And that charge basically is proportional to the displacement. Right, charge is proportional to the displacement. Because of the vibration, the piezoelectric element or triboelectric element is displaced. So that displacement is proportional to the current, and I is equals to dq dt. Right, so that's why there is a derivative relationship between current and displacement, or the voltage also you can tell. So that's why zero crossing of current correspond to the peak displacement. So whenever the zero crossing of current is happening or peak displacement is reached, either positive side or negative side, then and there I will be turning on the switch, so that this path will be kind of sorted and voltage will be flipped from positive to negative or negative to positive, depending on the current zero crossing or the equivalently peak displacement. Fine. So to illustrate further, you can see the corresponding simulation waveform. So this blue one corresponds to the current and green one corresponds to the voltage. So what we can see, till this particular interval, both voltage and current are positive, so power is positive. Now at this particular zero crossing of the current, I am ensuring the voltage should flip from positive to negative, so that during this interval, both the current are negative. As a result, my power will be positive. Again, here zero crossing is happening, then and there voltage is flipping. And as a result, again, we are getting the power waveform as the positive throughout. Is not it? So that is the beauty of this simple that synchronous switch harvesting on inductor circuit, right? So zero crossing of the current, at zero crossing of the current, we want to flip the voltage from positive to negative. Okay. So that is written over here. The switch is briefly turned on when the mechanical displacement reaches a maximum or a minimum corresponding to the maximum or a minimum of the voltage V delivered by the piezoelectric element. So as I mentioned few minutes back, that my current zero crossing and current I is equals to dq dt. Q is the charge, right? And Q is equals to C into V, right? And again, that Q is proportional to the displacement. So eventually what we can see, if I consider suppose your current as the sinusoidal signal, I sin theta, right? So then your charge will be what? Cos theta, is not it? If current is sin theta, so charge you can consider as a cos theta, and displacement will be also in cos theta. So that's why sin 0 degree, that correspond to sin 0 degree means 0. What is the corresponding cos 0? Cos 0 is 1. So that's why zero crossing of current correspond to the peak of the displacement or the voltage. So this is in terms of current. So for simplicity, you can consider that at the zero crossing of the current, we are ensuring the voltage will be flipped from positive to negative or negative to positive, so that throughout the positive power will be maintained. Right? Now, we need, of course, we are talking about the energy harvesting structure. So energy harvesting structure means we want to harvest the vibration energy into electricity energy using these elements and the subsequent circuits. So in order to turn on or turn off this switch, we should not depend on any other external circuit or external supply, because we are talking about the energy harvesting circuit. So energy harvesting means we want to harvest the vibration energy into electricity energy. For that purpose, we are using this SSHI circuit. In this circuit, I need to turn on or turn off a switch. So for turning on or turning off a switch, you can consider this as that BJT or the MOSFET. And in order to turn on or turn off, I need to trigger it. I need to bias this transistor. So for biasing the transistor, we should not depend on any external supply, because for biasing purpose also, whatever the energy is required, I should take that energy from the harvesting structure itself. That is the beauty of the cell power devices. Because if for this circuit, if I want to rely on any other external supply, then what is the point of doing the energy harvesting? Is not it? So that's why these are the kind of the different challenges during implementation. So where we want to make the whole system cell powered, including the circuit also. The circuit should be also operated in cell powered manner without depending on any dedicated power supply. Is not it? So eventually what will happen during this time, we can understand that eventually this will lead to larger or efficient output power if I incorporate this SSHI circuit. And at these triggering times, and because as soon as the switch will be turned on, you can consider the LC tank circuits, LC circuits will be formed, because of which your Q factor will be significantly affected and it will improve the overall harvested power. We can also understand from this waveform that power has been significantly improved because no negative part is there. And at the same time, in other way, logically also you can understand once it is switched on, then here you will be having the LC circuit will be formed, because of which the overall output power will be improved. Right? Now, ideally, my requirement should be sharp 90-degree transition should happen at this zero crossing. But practically, that exactly 90 degree may not get. There will be some that slope will be there. Instead of 90 degrees, it may be less than 90 degree. Because of that, some small amount of negative power can be there. And here is the innovations or the research using which we should improve these transitions, and we should make it as close as possible to 90 degree, so that completely a negative power will be eliminated. Okay, so these are the kind of the research flavors or the challenges. Okay, what are the important SSHI circuit features? You can see this is the piezoelectric or triboelectric equivalent circuit. This is the inductor and the switch. This is the SSHI part. This is the double bridge rectifier or the full bridge rectifier. This is the RC filters. And here you can consider that if we do not use this SSHI, this inductor and switch, then this red one or this brown one is corresponding to the output, power versus load resistance output. But when we incorporate this SSHI, you can see significantly the power is being improved. If I the idea about that. What are the important features of the SSHI circuits? As I mentioned, we should be having the automatic switching. For this switching purpose, we should not depend on any other external supply or any other external gadgets or devices. It should have automatic switching configuration. Switching delay. So the switching delay correspond to this delay. So ideally, I should have zero switching delay. So practically, our target should be by that proper suitable circuit scheme. We want to make the switching delay as close to. Then we should have the inversion factor. Inversion factor means from the negative to positive, the ratio V off by V on. That ratio should be as high as possible and close to 1. And the whole circuit should be completely self-powered without depending on any kind of external devices. So these are the kind of features required for implementing the SSHI. So now how to implement the SSHI circuit? So of course, this switch should be replaced with some BJT or MOSFET as per your convenience. And of course, this whole thing, there are a couple of important factors are there which you need to take into account. What are they? Suppose this is your piezo or tribo element. When it is exposed to the vibration, it is producing the electricity. And then from that output, we want to turn on or turn off the switch in a particular way. For that, what we need to do? We need to detect the voltage profile and we need to have the comparator. So for the how we can do that? Because when we want to turn on the switch, when the current zero crossing is there or correspondingly voltage peak is there. So for detecting of that, we need the voltage profile detector and the comparator which will compare with the zero for current and which will compare with the peak value in case of the displacement or the voltage. So that's why we should have the dedicated voltage profile detector and comparator block. Then we should have the transistor switch, and after that we have the rectifier and load part. For implementing this, we can come up with different kind of schemes or circuit configurations. In literature also different kind of circuits are available. So one of the popular circuit available is this is the kind of circuit which is representing the SSHI circuit. What is that? By looking at the circuits, don't get worried because this is not a very complex circuit. If you want to see one by one, you can see this left side, this current R and C that correspond to the piezoelectric nanogenerator or triboelectric nanogenerator equivalent circuit. Then you have this envelope detector. Then you have the voltage divider. Then you have the comparator. After that, you have the switch. And here is the inductor. So basically, this is the inductor and this is the switch. So this is the inductor and this switch correspond to this one. Now this subsequent, this part is required to make this switching happen automatically. Okay. Now if you look at, we will further illustrate. If you look at the right side, you can see this, you can understand this is the full bridge rectifier and RC filter part. Here you can see with respect to the inductor, this portion and this portion is symmetric. Only difference is that you can see the directions, or as you can see the diode directions, they are different. Here the diode is that the anode and cathode directions of these two diodes are opposite with respect to these two diodes. Then you can see here is the PNP transistors. Here you have this NPN transistors. Here is PNP, here is NPN. So only those differences are there. But rest of the things you can see with respect to this inductor, these two parts, left and right side are symmetry. What is its requirement? The requirement is you can understand when you talk about the sinusoidal vibrations, for example, it will be having one positive cycle and another negative cycle. So this, with respect to the inductor, this part, what I am highlighting through this laser pointer, this portion will be activated in the positive half, whereas these portions will be activated in the negative half of the vibration cycle. So at a time, either this part or this part will be activated. So what will happen eventually? Suppose this current, because of the vibrations, the current is produced, that is converted into voltage using this RC equivalent circuit, and across this capacitor, the voltage will be gradually that developing. So of course you can see, if you consider the voltage across the capacitor is VC1 and here you have the voltage as VP, there will be a lag between VP and VC1, is not it? So VC1 will try to track the VP. So up to the that up to the positive peak voltage, the VP will be greater than VC1. But when the voltage will go from the positive peak and come down gradually, then VC1 will be little bit greater than this VP, because this VC1 will be following the VP. So that's why this is called as the envelope detector. And this is called as the voltage divider. So voltage divider means the voltage across this resistance VR3 and this VP, they will have some difference. And here is the transistor. So this particular transistors, here you can see this is the PNP transistors. So here this is your emitter, this is your base, this is your collector. Right? So when this emitter voltage will be greater than the base voltage by 0.6 or 0.7, depending on silicon, if we consider as the silicon transistors, then only the transistors will be activated. If it is activated, then subsequently the diode will be forward biased and this will be activated so that the switch, this inductor will be basically coming in contact with this particular piezo or triboelectric device. And that will happen depending on the envelope detector and voltage divider and comparator configurations. And this will happen, the transistors will be turned on for a very small amount of time when the current zero crossing is happening. Current zero crossing corresponds to the voltage peak. So that's why here we are detecting the voltage peak. So voltage peak corresponds to the current zero crossing detection. That's why when the zero crossing of current is happening and the correspondingly when the voltage peak is happening in the positive half, then only at this particular instant, these particular transistors will be turned on and then inductor will be connected to the circuits and the SSHI configurations will be successful. In the negative half cycle, this part will be activated. So in the negative half cycles, when in the negative zero crossing or negative peak displacement or voltage when it will occur, then only this transistors will be activated. Accordingly, this diode will be forward biased and this particular switch will be also turned on and this inductors will be in contact with this RC circuit or the piezoelectric or triboelectric device, so that the flipping of the voltage will happen in both zero crossing of the current or equivalently the peak of the voltages. And in this way, this particular SSHI circuit is coming into the picture, right? So this is to give you the idea about the energy harvesting structure, specifically for the vibration energy harvesting structure, along with one example of its beautiful interfacing circuits and what are the challenges aspect. Okay, the further operations of this particular SSHI circuit is written over here. Whatever I have discussed, so those details are written over here for your quick reference and understanding. Right. So eventually the idea is that we want to implement this SSHI circuit, and implementation means nothing but your what I have discussed, that this topology essentially we are implementing so that I will be having larger output power, and in turn this will improve the overall efficiency of your circuit or overall system. Okay. Yeah. So till this point, I hope it is clear to all of you. So this is just to create the background of our discussion. Now we will move forward to discuss some of the interesting ongoing research activities in these directions, and we will explain or we will demonstrate different developed systems for different with respect to the different kind of energy harvesting structures, their interfacing circuits, cell power synthesis systems, along with the structural health monitoring applications. So till now, if you have any questions, you can ask. If not, we will proceed further. Okay. So in IIT Kharagpur, we have our lab that is named as MEMS, Embedded Electronics and Energy System Lab. In this particular lab, we are working on these different kind of activities related to the energy harvesting structure, different sensor systems, interfacing circuits, MEMS, embedded systems. Then you have this navigation systems aspects, as well as the structural health monitoring concepts. Okay, so let us give some glimpses of the ongoing research activities. So first, we want to develop, that vibration energy harvester. That is the first work we have started. Okay, so for working on the vibration energy harvesters, what we need? We need some transducers. For that, initially we have chosen the piezoelectric material. Okay. Now, to test it in laboratory scale, we need some vibration source, is not it? So initially when I started the work, so initially we did not have the necessary budgets or fundings when we just started work on these directions. So then what we did, instead of procuring the high cost vibration sources or the vibration shakers, we have started with a simple low cost speaker based setup. And this is the piezoelectric material we have chosen to start the work in the direction of piezoelectric energy harvester. So I am giving you the glimpses from the very scratch or the beginning, and then we will show you the current status so that the early career researchers will have a idea or motivations that how to start work on your allied interested field, and how to start the research from scratch up to the that modern state of art activities or the research areas, right? So we have started with this commercial piezoelectric device, which is made of this PVDF material. And this is the small low cost speaker we have considered. This particular speaker we have energized through a small power amplifier and the function generator or the signal generator. And we have basically, when we apply the sinusoidal signal with the target frequency and amplitude, then through the power amplifier, that is basically activating this trigger, that speaker, and that starts vibrating. And on top of this speaker, we have considered one small this PVC tube based material on which we have mounted one this aluminum plate, and on this tip of this aluminum plate we have put this piezo sensor. So when it is exposed to vibrations, we are that taking the output voltage across this piezoelectric material, and we can see that this is the typical piezoelectric output which I can get from here. And also we have mounted one accelerometer structure on this aluminum plate so that we can have some map that what kind of actual the acceleration sensor is giving the output with respect to vibrations, and how the piezoelectric device is giving the output. So just to get the idea, we can show the piezo output and the accelerometer output in the same plot. And this is the typical configuration. So here you can see this is the speaker on which you have mounted the cantilever and the piezoelectric device. Now to activate or trigger the speaker, we are using the power supply, and so this is the power amplifier, this is the function generator. So function generator is connected to the power amplifier, and for giving the required power supplies, we are using the dedicated DC supply to give the power of this to the power amplifier. Then this output is fed to the speaker, because of which it is starting vibrating, and because of that vibration the piezoelectric is generating the output, which I can measure through that digital storage oscilloscope. And also we can connect the piezoelectric output to the signal conditioning circuit, which can include initially the simple bridge rectifier circuit, and using that circuit we can store the energy in some high value capacitor, and using that storage energy we have tried to drive some simple resistive load or some LED to start this work related to the vibration energy harvesters, right? Where we have taken a simple speaker as the vibration source, a simple commercially available piezo sensors, and just we have got the voltage output because of the vibrations. Then I have connected a simple bridge rectifier to get the DC output, and finally use it to power some resistive sensors or the LEDs. That is just the very initial proof of concept that okay, yes, the energy harvesting concept is working. Then we gradually started working on different kind of improvement aspects. Initially, we have got some 782 microwatt across this 3.3 kilo ohm load resistance for this particular scheme. Then we have carried forward to improve the overall performance of the piezoelectric device. Now we have started working on the design improvement. Okay, the initial concept is working, that very basic preliminary concepts. Now we have started working on the design aspects. So suppose if I have a cantilever over here, and if I want to extract larger output power or larger energy from the vibration, then what kind of design modifications we can do? What we have thought of, or what we have come up with, that if I incorporate some holes in the cantilever, then because of that hole, the cantilever stiffness is significantly affected, and that is affecting the overall resonant frequency as well. Eventually, that is helping us to achieve larger output power from the piezoelectric device which we have installed or mounted on this particular cantilever. So that's why we started working on this calculations of this resonant frequency using this Rayleigh method. We have come up with some closed form expressions that because of the incorporation of the whole, how the closed form expression looks like for the resonant frequency. Then we have done the corresponding simulation in COMSOL multiphysics by applying different vibrations, what kind of stress pattern is coming, what kind of output voltage is coming from the piezoelectric device. So then we have compared that with respect to our theoretical resonant frequency analysis, how it is coming closer with respect to the analytical value. So we can see that analytical value and this simulations values are quite close to each other, and percentage error is maximum error is 13%, but the other error is only 1.2% and 5.9%. So these are just initially the theoretical study, and our objective is to reduce the resonant frequency so that in that low frequency we can extract larger output using the piezoelectric device. So that's why we are doing this kind of analysis, and from that we have started working on different aspects. Now we can see that if we, for this same structure, if we plot the stress versus the length, then we can see in the whole region we can get larger stress variations, because in this whole region, because of that whole, our stress profile is that improved, our resonant frequency profile is improved, and which is eventually helping us to increase the overall output power from the piezoelectric device, because the output power depends on these factors. So we can see by creating circular hole, rectangular hole, without hole, we can compare the performance. So we can see when no hole is there, the profile you can see that is kind of the flat profile, but when the hole is there, you can see the peaks are there where the larger stress is getting generated. Because of the larger stress, we can get larger output from the piezoelectric device, which you have deposited over here, right? Then this is the simulated view and this is the practical view. In the practical cantilever, aluminum cantilever itself, we have created the holes and mounted the cantilever, that piezoelectric device, and we have verified the performance, that how this, if I do not incorporate hole and if I incorporate hole, what kind of differences we can expect in terms of its piezoelectric output, energy, power, and so on. Right. So here you can see the experimental setup, that is without hole. This is the rectangular hole. This is the circular hole, and we can see the plots, that voltage output of the piezoelectric versus frequency. So you can see that if we incorporate the hole, so then of course we can see your this red one correspond to without hole. You can see the voltage versus frequency characteristic. Red one is for without hole case, and black and blue correspond to the two hole case. Black correspond to circular hole and blue correspond to the rectangular hole. We can see because of the incorporation of the hole, the more voltage we are getting across the piezoelectric device. Is not it? So then here we have the voltage versus for different structure. For classical cantilever, that means without this hole, what kind of output we are getting, and for rectangular hole and circular hole, what kind of output we are getting, and we are comparing our experimental output with to each other. So in this way, we have step by step, we have moved. First, we have proved the concept. Then we have started working on the design aspects, and further, once the design is done, that we have got the idea that yes, the holes are having definite important roles in the performance of the piezoelectric energy harvester. So now we have started working on the hole optimization. So what could be the hole, that optimum dimension, the typical length, width, locations, what can be the typical that dimensions, optimum dimensions of the holes. With respect to that, we can see that here this is without hole structure. Here we have a hole, non-optimized hole, where just a simple hole is put, and here you can see this is the optimized hole. How we have got this? For this is the typical flowchart we have followed, that we have just here here couple of parameters are there, that what is the location, where should we put the hole, and this is correspond to the proof mass. So this correspond to the free end, and this correspond to the fixed end. So hole should be towards the fixed end. Okay. And what is the typical dimensions for that? Here we have what will be the location, what will be the length, what will be the width. So all the parameters at a time we cannot change. Then the analysis will become more complex. So that's why we have done step by step. First we have considered, okay, let us fix the location at 100 micrometer from the fixed end, then fix the width and vary only the length. Then we play around that keeping the length fixed, width fixed, varying the location. Then again keeping the location fixed, length fixed, varying the width. So likewise, different ways we have carried out the analysis and simulations and come up with the beautiful ratio for which we are getting the optimum hole dimensions. So this is the typical flow chart, and what we can get, that suppose this output voltage versus the particular ratio we have come up with, that length of the hole divided by hole cantilever length. So normalized length, this is the length of the hole and this is the length of the cantilever. So we have come up with the normalized ratio between what? Hole length versus cantilever length. And that ratio we have come up with from this optimization. If I go on varying the ratio, I can see there is a particular ratio around 0.4 for which I am getting the optimum output voltage from the piezoelectric device. Okay, so that is for cantilever. That is from for one typical structure. If I talk about the power, here also you can see this is the voltage versus ratio plot. Here you have the power versus ratio plot. Here you can see typically around 0.4 ratio, we are getting the optimum power or optimum voltage from the piezoelectric device. So that's why we have fixed that, okay, let us put this is the typical optimized hole dimension for which we will be doing the subsequent analysis. So in this way, we have carried out the analysis step by step. Now we have further focused on our that more dedicated develop energy harvester structure and setup, and gradually we are moving forward to develop the cell power sensor system, right? So what we can see over here, so this is the typical experimental setup where you can see this is the, so initially we have tested our device on the speaker, and later on we have, when we got the, based on our initial work, when we got the funding from the government agencies like ACRB or ANRF, that we have subsequently used for basically carrying out the experiment in more controlled manner and with more variation, right? So here you can see that this is the circuits, the typical SSHA circuit or the improved SSHA circuit we have built in the Vero board. Then we have designed the PCB on which we have that designed our whole interfacing circuits and put our that piezoelectric device and exposed to the vibration using the seeker, and then we are that this particular function generator is used to excite this vibration seeker so that the required vibrations we can generate, and from that DSO we are getting the output voltage across the interfacing circuit. And so typically the vibration seeker is used as a source. PZT based lead zirconate titanate material based piezoelectric device we have chosen with the model number PPA 1011 1014. These are the piezoelectric device which we have used for the experiment. And interfacing circuits, what we have used is the modified SSHI circuit, right? So typically, just you can see the this response. So you can see that when we are exciting this particular seeker through the function generator, it is vibrating. And this is the typical excitation amplitude which we have given to excite this vibration seeker. And from this oscilloscopes, we are getting the output voltage and also we are getting the rectified output voltage from our SSHI circuit, right? So this is to give you the experimental idea. Then again, we can see now using this PCB also we have done the experimentations, and you can see that this is the kind of waveforms what we can get from the oscilloscopes. Here different kind of waveforms of the SSHI circuits we can see. Okay. So now based on this experiment, just to give you the idea about the experimental results, if I apply some 5G vibration and 24 Hz excitation frequency, you will be surprised to see that 55.6 volt peak to peak output voltage we are getting from the piezoelectric device. The experimental setup and video for which we have shown, for that this is the typical open circuit output voltage what we are getting. Now when we are connecting the SSHI circuit, modified SSHI circuit on with this piezoelectric device, you can see that this is the typical input signal to the vibration seeker, and this yellow and maroon, these correspond to the that output, the positive and negative output side. That is basically the typical power output of the SSHI circuit, and this is the rectified output voltage. So we are getting around 12.1 volt rectified output voltage, which is good enough to meet the power requirement of different low power devices. So of course we will be using the regulator circuit to scale it down from 12.1 volt to 3.3 volt or 5 volt as per our requirement. And typical harvested powers we are getting around 1.5 milliwatt, which is good enough to meet the power requirement of the low power electronic devices or the gadgets or nodes. Okay. then we have worked on the interfacing circuit modifications. So SSHI circuit methodology, that basic principles we have discussed, right? Now what we have done, you must be aware about this MPPT logic, which is very widely and commonly used for the solar energy harvester. What we did, this MPPT logic, we tried to incorporate with our SSHI concept and then come up with a new integrated interfacing circuit for piezoelectric device in order to get larger output and efficient performance, right? So what we have done, you can see this is the typical piezoelectric equivalent circuit, and this is our SSHI circuit, and this is the full bridge rectifier. So till this already we have discussed earlier, we have seen this typical SSHI circuit. Now what we have done, with respect to this, we have incorporated this analog MPPT logic, and using this analog MPPT logic, what essentially we are doing, if I use only SSHI, then only SSHI is not ensuring the maximum power point tracking. Now with the incorporation of MPPT, what we are doing, essentially we are able to eliminate the negative power from the SSHI using the SSHI, and using the MPPT, we are able to improve the power tracking performance. So that eventually by integrating both the circuit topology together, we are able to achieve larger performance, and we are using one DC to DC converter, we are using one voltage monitor or voltage supervisor, and finally we are connecting the ADXL sensor. Okay. Yeah, so any question, please mute yourself. I think, yeah. So you can see that through this is the typical circuits which you have proposed and which you have developed. This is the which you have interfaced with the piezoelectric device, and this is the load, sensor load, which we want to drive using this overall system. So what we have done using this voltage monitor, we have driven this particular acceleration sensor in completely self-powered mode.
Sir, you have unmuted, sir.
Sir, please unmute yourself.
Yeah, can you hear now?
Yes. Yeah,
so how long ago it happened?
Just 30 seconds, 1 minute, less 1 minute.
Okay, fine. Okay, thank you. So now hopefully you can see the screen and you can hear me.
Yes, sir.
Okay, fine. Thank you, sir. So what I was saying that the SSHI topology already we have discussed. Then what we propose, this analog MPPT logic we have incorporated with the SSHI, and by integrating both the circuit together, we are achieving larger performance. And what eventually we are doing, using this piezoelectric device, when it is exposed to vibration, then this output is connected, passed through the SSHI and MPPT logic, and finally through this voltage monitor, we are connecting the output to the sensor for driving it. What we are doing, that suppose at specific interval, we are feeding the ADXL 335 accelerometer sensor, and suppose I want to monitor the vibration of a particular vehicle. Then what I will do, I will install this vibration sensor, acceleration sensor, and I will install my energy harvester along with the interfacing circuit. So energy harvesters will convert the vibration energy into electricity energy, and that energy is being used to power up this acceleration sensor. And in this way, beautifully, we have developed the self-powered acceleration sensor for measurement of vibration. We will show you the results as well. So this is that PCB which we have developed, which includes the SSHI along with the MPPT circuits together. And this particular circuit is interfaced with the piezoelectric device. You can see this is the interfacing circuit. This is the piezoelectric element. This is connected to the circuits. This is the seeker on which we have mounted our piezoelectric device. When it is exposed to the vibration, then piezoelectric starts vibrating, and through the power management circuits, we are getting the output over here. So what we are doing through this voltage monitor, what kind of output we are getting? So suppose the voltage monitor is like that, that I want that when my output voltage across this storage capacitor is going beyond 3.3 volt, then the acceleration sensors will be connected to my circuit and it will be operated in self-powered mode. Now, as soon as I connect it, so the voltage level will gradually reduce, and as soon as the voltage level reduces beyond a lower threshold like 2.65 volt or 2.7 volt, then again this sensors will be disconnected. Then again it will start charging and voltage when it is exceeding beyond 3.3. So likewise, it will having based on the two thresholds, this acceleration sensor is operated successfully in self-powered mode in discontinuous manner. Discontinuous manner, minute interval, the sensor is connected, the data is captured, and the data is transferred to your desired location so that you can monitor the vibration in self-powered manner, right? So here is more better views. Like you can see that this is the storage capacitor. So when the storage capacitor output is greater than 3.45 volt, then the reset button, so it is getting activated and the accelerometer is getting triggered. And you can see in this portion, this is the zoomed view. This is the beautiful accelerometer output, which is operated completely in self-powered mode without any kind of battery or any kind of power supply. Right now, again, when the voltage is going beyond 2.4 volt, this is again disconnected and accelerometer is disconnected. So in this way, in discontinuous mode, we are successfully able to run it in the self-powered mode. The same thing has been tested in the bike as well. So in this scooty, as you can see here, we have mounted our energy harvesting setup as well as the accelerometer, and I want to monitor the vibrations of the bike. So for that purpose, I need an acceleration sensor. Now to run that acceleration sensor, I need some power supply. Here what we are doing, we are not using any power supply. Rather, we are using our proposed energy harvesting structure along with its SSH MPPT circuit, and using that, we are developing that self-powered energy harvester systems and that self-powered sensor system. So using that energy harvester output, we are able to drive the acceleration sensor in self-powered mode. And we can see, and here we have compared our proposed circuit output with respect to the existing circuit output. So you can see this CFG4, that is our proposed output. That output power has been significantly improved with respect to the conventional circuit parameters. Typically around 295 microwatt power we are harvesting. Accelerometer is operated fully self-powered mode. Typical accelerometer output, what we are getting from here, 5.7 G at 24 Hz, and accelerometer data we are able to transmit it at every 1 minute interval in completely self-powered mode. Okay, so this is one of the beautiful demonstrations what we have got. Further, we have also demonstrated the self-powered accelerometer, a complete setup. So in this case, that setup was mounted just on the pedal stand of the bike. But now we will show you that on the actual scooty also, so we have mounted this particular setup where we have come up with this mounting base. Then this is the piezoelectric device. This is the modified SSH circuits along with the accelerometers. This is the top view of this arrangement, and this whole arrangement we have mounted in this bike, this rim arrangement. And when the bike vibration is there, then the piezoelectric energy harvester is converting that bike vibration into electricity. That electricity energy is basically used to power up this accelerometer sensor, which is giving us the accelerometer output. Okay, so custom mechanical setup, self-powered ADXL33 accelerometer, ADXL35 accelerometer, and you can see this is the accelerometer output. And in this way, we are successfully able to demonstrate the working of this ADXL335 accelerometer. Completely, this is powered based on the bike vibration, and this vibration is converted using this electricity energy using the SSH circuits and the piezoelectric device, and that power we are using to run this particular sensor, and this is the typical sensor output. Okay. So after that, we have also come up with the self-powered pressure monitoring system. So for this is the typical circuits which we have fabricated, that self-modified SSHA circuits. This is the piezoelectric device, and some novel switching techniques are there. This is the typical pressure sensor, and this is the novel switching TPMS circuit. Here what we are doing, here also we have made one custom made setup and mounted this whole setup in this scooty arrangement, and that connecting valve, where basically I want to monitor the tire pressure. So connecting valve will be connected through that pipe arrangement to this particular sensor, that circuit board. And here what essentially are doing, the objective is that the pressure of this scooty tire will be monitored. This pressure sensor, and this pressure sensor is completely self-powered by your piezoelectric device along with the energy harvesting circuit, right? So what essentially we are doing, that in this case we are able to successfully drive it in self-powered mode, and the tire pressure we are monitoring through the pressure sensor, which is operated in self-powered mode using the energy harvester setup. So here it is having the indication that if the tire pressure is less than the threshold, so then it can give you some that red LED warning. If it is good in the above threshold, so then it will be indications of the green LED. Likewise, these arrangements we are making. So typically here we are harvesting around 1.59 milliwatt power, and in laboratory scale also we have tested it, and then on the bike vibrations also we have tested it, and we are able to successfully drive it in drive for around 11 minutes using this particular setup. Okay, so this is again another self-powered pressure monitoring system using the energy harvesting structure. Now coming to the hybrid harvester. Hybrid harvester means what? Now we have discussed individual harvester, individual piezoelectric harvesters mainly we have discussed. Now, if I want to talk about the hybrid harvesters, then what we can do? We can connect solar, piezoelectric, thermoelectric, electromagnetic, multiple harvesters we can integrate together through the dedicated interface circuit, so that we can store larger energy in smaller time, and we can drive more devices together for larger amount of time. So that is the concept of hybrid harvesters. We have also worked on the hybrid harvesters where we have demonstrated the piezoelectric and electromagnetic hybrid harvester together. You remember we discussed about the methodology or principle of electromagnetic type vibration energy harvesters. So here we can see this is the 3D printed cylindrical tube which we have designed, inside which we have put these couple of magnets, and this hollow cylinder is we have put the cap in both the sides, and in between this you can see the coil is wrapped around. So when this whole frame is subjected to vibration, there will be relative displacement between this magnet and the coil. As a result, the EMF will be produced, and in that way these electromagnetic harvesters will be working. Now what we have done, we have hybridized both piezoelectric and electromagnetic hybrid harvester together. What we did, you remember in our SSHA circuits, we have talked about one that inductor. What we told, that one inductor and one switch was there in the SSHA circuit. You remember? Here what we are doing, in order to hybridize it, that inductor, passive inductor, we are replacing that passive inductor with this active electromagnetic coil. And in that way, through this SSHA circuit, we are hybridizing the piezoelectric and electromagnetic together. Okay, the rest of the circuits are similar. Only changes what we have made, instead of using the passive inductor in the SSHA circuit, we are using the electromagnetic coil over here, so that this is your electromagnetic coil and this is your piezoelectric device. When both are subjected to vibration, then what is happening through this SSHA circuit itself, this is acting as the active inductor, and because of which we are getting larger output power. And eventually in this case, we are hybridizing both the piezoelectric and electromagnetic device together. And this is the typical output response. This is the electromagnetic module. This is the raw output. This is the output versus time for F equals to 18 Hertz. When we are using only piezoelectric device, the rectified output is 6.1 volt. Now, when we are using the hybrid structures, the output has increased from 6.1 to 7.7 volt, right? So we can see the beauty of the uses of this hybrid configuration. Here again, we can see that for 10 Hertz, the output voltage has changed from 1.3 volt to 4 volt because of the incorporation of the hybrid configuration. And this is the typical that power improvement with respect to the load resistance. There also we can see, because of the hybrid behavior, we can get significant power improvement in the typical load resistance in the range of 150 to 300 kilo ohm. In this range, we are getting good amount of power improvement with respect to the individual harvesters for the hybrid harvester concept. Okay. Now we have discussed about the piezoelectric and electromagnetic. Now we will discuss about the triboelectric also. You remember we discussed about three transduction mechanism: piezoelectric, electromagnetic, and triboelectric. Piezoelectric and electromagnetic we discussed. Now we will discuss about the triboelectric. So triboelectric, we said this works based on the two different materials. One is positive, another is negative, and this orange color, these correspond to the electrodes. So when they will be coming in contact to each other and contact separation will happen. Because of that, we will get output voltage across the electrode. What we have considered for the piezoelectric, one material we have considered as the mica, another material we have considered as the PVC, and aluminum is considered as the electrode. When they are coming in contact and separation continuously, it is producing the output voltage. For that purpose, we have used one big shaker. So now by this time we have got more funding and we have procured another big vibration shaker along with the whole setup, vibration controller, vibration power amplifier, the data analyzer and everything. And now what we have done, we have made one wooden made custom setup to test this triboelectric, to carry out the triboelectric experiment. So here you can see on the top of this shaker, we have mounted one aluminum plate on which we have put the PVC material that is acting as one triboelectric material. On top of this wooden base, here we have put electric material, and then this, you can see this whole setup that is basically closed over here, right? So here you can see, so on the on the base of the vibration shaker we have one material, and on the top we have another material. So that top is put on the this base of this wooden frame. So this base is fixed. Now when this is vibrating, so it is coming in contact separation, because of which the output voltage is produced across the electrode between the mica and the PVC. Okay. So here typically one low drop diode equivalent circuit we have used as the interfacing circuit for the triboelectric device. So this is again the whole setup. Here you have this vibration controller, power amplifier. This is the wooden setup inside which we have the shaker. This is the DSO from which we are getting the output. This is the LDD interfacing circuit. You can see this is the typical raw output from the triboelectric device, and raw output we are getting around 19 volt at 29 hertz. And for that, using this rectifier based circuits, our rectified output we are getting 4.92 volt, which is good enough to meet the power requirement of the low power devices. Using this voltage and the corresponding energy, we are successfully able to drive one MAX 44009 light sensors. So you can see that this is the typical light sensor, which is completely driven in self-powered mode through this triboelectric along with its interfacing circuits. And just for transferring it data and observing it in the serial monitor, we are using the Arduino just for plotting this sensor output and sensor data. But other way, the sensor is completely driven in self-powered mode, and for driving it, the energy is coming from the triboelectric device, which is converting the vibration energy into electricity energy and storing it in the that supercapacitor through its interfacing circuit, which is used to power up the devices. Okay. So till now we have discussed about the vibration energy harvesters. We have discussed all the techniques: piezoelectric, triboelectric, and electromagnetic. Now let us discuss with respect to the solar energy harvesters what we have done. Solar energy harvesters, people have done different lot of activities, mainly for the high power application, grid applications, those kind of high wattage applications. But in this case, we are demonstrating one that low power applications, and the research flavor what we want to incorporate over here, the integrated dual control framework for self-sustained single stage solar energy harvesting system. So what we have done, this is the small solar cell around 2 wattage power rating solar cells we have taken for low power applications. And here we have proposed one 3-level boost converter and one dual control scheme. Dual control means where basically we want to control the maximum power point as well as the output voltage. Both should be regulated together. So basically for this purpose, we have used the perturbation and observation based MPPT technique and integrated it with the PI control strategy in order to regulate the voltage and power both in integrated control framework. Now, for this purpose, we have done both the laboratory experiment as well as the rooftop experiment. This is the small PV cell, and this is the artificial light. By changing its intensity, we are that carrying out the experiment. And this is the typical dual control framework circuit where we have the MPPT logic running in a MSP 430 microcontroller, as well as the PI-based control logic is also there, and both the control logic are happening simultaneously in dual control framework. And using that, we are able to drive different sensors and actuators successfully in self-powered manner. In the rooftop experiments also we have done, where we have demonstrated one ventilation vent prototype. A little bit later, we will discuss it in more detail about this particular prototype configurations. This is the typical output response. We can see that with respect to this rectified output, we are able to drive this different sensors, this humidity sensors, temperature sensor, light sensors, so many sensors we are able to drive successfully using this dual control framework. We are getting the around maximum boosting efficiency at 87%, and circuit loss is only 20%. MPPT tracking efficiency is very good at around 99.98% with tracking time of 63 milliseconds. Then after that, we have demonstrated another very beautiful this experimental concepts where this ventilation vent, so automatic that ventilation air vent, intelligent air ventilation applications we are trying to demonstrate here. What is the objective? So suppose nowadays we are accustomed by living at the AC room. So when that suppose because of the long term uses, if inside a room the the undesired gases concentrations gets increased beyond a threshold value, then what will happen? Then automatically the ventilations will be opened. As long as the those polluted airs quality is there, the ventilations will be opened. And when the pollutions will be reducing, and there will be no more pollutions, then again the ventilations will be closed. And all these things should happen in self-powered manner, in automatic intelligent way. For this purpose, we have taken help of this solar cell concepts, where what we have done, you can see that this is the dual control framework what we have done with. And here one small motor we have considered. On this motor, one small ventilation prototype, one rod arrangement we have put, right? And here is one gas sensors. So whenever, for testing purpose, just some smoke sensors we have considered. And whenever the smoke is detected, then and there, through this dual control framework strategy, this motor is rotating and the ventilation vent is opening. Again, when the gas sensor, when there is no smoke, then gas sensor is giving low signal. Accordingly, again, the ventilation is becoming closed. So all these demonstrations has been done with respect to this small that solar cell prototype, where you can see that signal from smoke sensor, when it is detected, the motor that is getting activated and vent is becoming that open. And when the sensor output is becoming low, again the vent is becoming closed. So likewise, this scheme we have implemented using this self-sustained solar energy harvesting system itself. Okay. So this is about the solar energy harvesting part, and of course for the low power sensing, low power devices applications. So I hope that till now it is clear to all. Now we will venture into the last application, that is the application towards AI ML enabled structural this time. So how we have discussed, we have started with very basic generic background about the energy harvesting concepts to create the background to all the mixed audience having diverse background. Then we have started discussion on our ongoing research activities step by step. Whatever the theoretical concepts or the background knowledge we have discussed, all the corresponding demonstrations and proof of concepts we have demonstrated. And finally, we will be demonstrating the application towards AI/ML enabled structural health monitoring application. Okay. Here, what is the idea? Suppose the structural health monitoring purpose, we have considered two bridge prototype. Okay. The objective is, suppose I have, suppose very busy bridge is there. Suppose Howrah bridge or very busy bridge is there where regularly lot of vehicles are going by, passing by, and we are not sure what is the health conditions of the bridge. So for that purpose, we will be installing different sensors like stress sensor, vibration sensor, temperature sensor, and so on, which will continuously monitor the different performance mechanical parameters of the bridge, and they will be transmitted wirelessly to the server and in the control room, so that we can monitor from the control room what is the bridge status. So for this purpose, how the AIML is coming into the picture and how the energy harvesting is coming into the picture, that flavor we are going to discuss. So for that purpose, what we have done, we have considered two bridge, like two small bridge prototype, lab scale prototype we have made. This is one bridge where you can see two holes are there, and here another bridge where total 5 holes are there. We can, or cracks are there also. So we can consider that this is relatively healthy bridge and this is unhealthy bridge where multiple holes has been created because of longer uses. Now our objective is how that energy harvesting concept and AIML is coming into the picture to monitor the health of these two bridge and how it can tell whether the bridge is healthy or unhealthy. For that purpose, what we can do, we can install couple of sensors on these bridges, and we will be acquiring the real-time sensor data. Then we will be processing the data and we will be extracting the important feature. After that, on those data, we will be applying our machine learning models for fault predictions. Then we will be detecting if there is any anomaly. Based on that, we will be predicting the health, whether it is good or bad. And also we can predict that what is the typical time to failure estimations. And finally, all these informations we can visualize live and we can give the corresponding alert. We can make some GUI to see all the data visualize purpose as well. Right? So what we have done so far, we have considered this kind of aluminum bridge where a couple of sensors like accelerometer sensor, gyroscope, temperature sensors, ultrasonic sensor, acoustic sensor, teal sensors, strain sensors, those kind of sensors we have mounted on this bridge at different location. And this is the same sticker which you have seen earlier, that vibration sticker. On top of that, we have mounted the bridge, and on top of that, we have installed different sensors. We are continuously monitoring the sensor data for both the healthy bridge as well as the unhealthy bridge, and those data we are using to process further to basically classify whether the about the bridge configurations, whether it is healthy, unhealthy, and if it is unhealthy, how much the typical the time to failure. Those predictions also we can do. So those aspects we have done. So here, what is the role of the cell pod or energy harvesting concepts? We can install the energy harvesters which we have developed so far in the vicinity of these sensor nodes, and because of the available vibration, those or the solar energy, we can convert the available vibration and solar energy into electricity energy, and using that we should be able to drive all these sensor nodes in self-powered mode. And finally, from these sensors we will be capturing the data. Those data will be processing, different machine learning models will be run, and we will be able to classify whether the bridge is healthy or not. That is the overall concept throughout, right? So what we have done, we have carried out the experiments with different random vibrations. We have put through the Sekar and captured all sort of data to create our own database where different vibration pattern, different temperature environment we have created to capture different data. Then those data we have processed it further. After removing the noise from those raw data, we have processed them, and based on that healthy bridge data, unhealthy bridge data, we have come up with different clustering problems. So basically using k-means clustering, we have got around 9 cluster we require to basically classify the bridge health properly. So like cluster 0 correspond to low temperature, short distance, light load. Then maintenance action means normal, regular inspection. Cluster 1 means moderate temperature, heavy load, high sound. That can be considered as the dangerous. And maintenance means we need to reduce the load and inspect it closely. So likewise, couple of clusters we have come up with different variants of data. Short distance means with respect to the critical zone, what is the safe distance, Euclidean distance, that kind of concepts. So based on that, we have come up with the different clusterings. Then primary classification model we have considered as the support vector machine algorithm, and to enhance the reliability of the overall techniques or methodology further, we have also considered the ensemble modeling learning kind of models, where a couple of backup models are there, under which we have used the random forest classifier, KNN, ADA boost, gradient boost, logistic regression, and so on. And based on that, one main model and couple of backup models are there, and we have carried out one pipeline technique kind of analysis, where one is the that primary model, another is the secondary models, and every time the based on the data set, the whole iteration is going on, and from all the models we are calculating what is the accuracy of each of the model, and based on the accuracy we are giving the different weightage to different model, and then finally whichever are having high scores. So those models we are considering for the final prediction, and based on that we are successfully able to predict whether the bridge is healthy or unhealthy, how much is the typical time to fill your estimations, and so on. And overall classification accuracy we are getting in the range of 94%. Right. So this is about the last applications for our AI/ML enabled structural health monitoring, and also we have discussed how the energy harvesting can be incorporated over here. What are the different research scopes in these directions? You can think of different suitable advanced material synthesis, new design with respect to the harvesting structure, new design of power management circuit, hybrid energy harvester design, cell power system development, new application domain, and finally AI/ML based structural health monitoring for predictive maintenance. Okay, so I would like to acknowledge our sponsoring agency like ACRB or ANRF and IIT Kharagpur. Also, of course, the different students have worked on the different aspects of these works, where I should mention about our Dr. Priyabrata Biswal, then Sovik Khan and Mukund Mata as the PhD students, and a couple of MTech students are there, including Akash, Aman, and Tejaswini. And of course, I will be acknowledging our affiliated center and the Advanced Technology Development Center, IIT Kharagpur. Right. So with this, I am concluding my discussions. Now, please feel free to ask questions. So the way in which I have tried to emphasize is that I have started with a very generic background about the topic to give all of you about the basic background knowledge. Even if some of you are already working in this field, for them also, I believe this will give you a good opportunity to carry forward your work, and also you will be accustomed with different new horizons and new activities in this technological domain. And who are having that no background, for them also I believe this will give you a good amount of that exposure to this particular new field. I have initially given created the background by giving the descriptions and background of different techniques or the methodologies. After that, I have discussed about our ongoing research activities in our MEMSense lab, where whatever that theoretical background concepts we have discussed, all of them we have shown the corresponding proof of concepts along with their results. And finally, we have demonstrated one applications for AI/ML enabled structural health monitoring as well. So now please feel free to ask questions if you have any.
Very nice presentation. So is there any queries from participants side?
Yes, sir.
Yeah, please tell. Dharmendra Kumar.
Yes, sir. First of all, I'm thankful for you, sir. Your presentation was very good and very nice. Really, it was very helpful for us. And one thing, sir, that I'm also working in piezoelectric material. What have what have you did? But the problem is that
Which material? Triboelectric.
piezoelectric material. Yes, sir. For
Piezoelectric or
energy
triboelectric?
harvesting. No, piezoelectric, not triboelectric.
Okay.
The
What
problem
material
is that
exactly?
after. Yes, sir.
Which material you are working on?
Piezoelectric materials, sir. Actually, we are just measuring the food step, harvesting the forest with the help of food step. We are harvesting the energy, but we are unable to capable store energy in large amount. Only I am capable to just build the small amount of LED and one just optical mouse. Is there any way to increase the to store more energy?
Yes, yes. So that's why we have discussed a couple of methodologies. So now, can you tell that what is the specific material you have chosen?
Actually, sir, I have buy it from another from US. We have just purchased it. I just tell you.
Okay. So the material you have purchased or the sensor you have purchased?
No, sir, I purchased the piezoelectric plate. Piezoelectric seat is there. Just like your tiles, there is a piezoelectric seat, circular plate.
Yes.
We have purchased the piezoelectric plate. It will be just plate, sir.
Okay. And have you used any kind of interfacing circuits, or
Yes, sir.
only
We have
some
used.
capacitor and bridge rectifier you have used?
Yeah. Only capacity, the bridge rectifier and super capacitor for energy to store the energy.
Yeah. So that's why, as you can see, that if you use only the this bridge rectifier, then you may not be able to store it in larger way. Like you can for that you should use, because the interfacing circuit plays very important role, is not it? So that's
Yeah.
why, and I understand that so
It means
some people can.
I am not able to store my full energy. It will be lost. Somewhere there is a loss.
Yes. So I suggest that you can one is that, like because I understand that when you are developing or working on this area, so then some
Yes.
people will be having expertise in material, some people may be having expertise
Yes,
in that design, some people may have
yes,
expertise
sir.
in the circuits. So it is quite challenging that you should have the expertise in all the aspects, including structure, circuit, system, everything. But still, I will suggest that, of course, that you may have interest more in the because the material anyway you are purchasing, so you are not making any contributions to the material part, and the
Yes, sir.
sensor
Yes, sir.
part. That sensor part also, you are basically, by the way, that what is your designation? You are
System professor.
okay. So yeah, so I understand that so you can start working on the circuit aspect, where initially, like the simple bridge rectifier you can use, but using that bridge
Okay.
rectifier, as you can see, that there is not much more energy you are able to store. And also, if you
Yes,
want to carry forward your research activities, then at some point of view, or with respect to some portions, you have to show your contribution also. So in this way, what
yeah.
you are doing there, the material you are purchasing, so sensor you are not building. If you can,
Yeah.
there is one way is that you can come up with some design aspect. Maybe the same
Yeah.
material, you change your design dimensions and put it in on some another platform, where you can make with different design dimensions, change the geometry by doing some simulations, and then by changing that, you can have one options to increase the overall performance, and second options will be to work on some dedicated circuits. Like there are
Okay.
lot of circuits are there in the literatures, where you can see that at least you can take up initially some circuits, and like the SSHI I have told, we have LDD circuits are there,
Yes, sir.
ACC circuits are there. So lot of interfacing circuits are there, people have worked on. So so you can go through them, and you can choose the one efficient circuits, and that you can try to incorporate and integrate with your structures, and try to see the performance improve. And that is
Okay.
second thing. And third thing is that you can try to use larger value of supercapacitor. Like you can have
Okay.
some 0.22 farad capacitor. So typically your capacitors you are using which range? Some 100 microfarad kind of value, or what?
Yes, sir. Yes, sir. Yes, sir. Yes,
Yes.
sir.
So that value also you have to increase, because 100 microfarad, that will quickly charge, but at the same time it will quickly discharge also.
Could be
So
discharged. Yes, sir.
your open circuit voltage can be very high. Your open circuit voltage, even you can get 30 volt, 40 volt like this. But as soon as you connect your this bridge rectifier or the circuit, you can see the output is suddenly dropping down. So that is
Okay.
because it is drawing the low that current very quickly, very fastly. So that's why you need to have larger value of supercapacitor. So if you use large value of supercapacitor, at the same time it will take more, you can think of. And finally, you can work on the interfacing circuit part. Okay.
Okay, sir. Thank you.
Okay. Welcome.
Thank you, sir, for your very nice presentation and very good demonstration. I think that is very much useful for all the participants. And also, I thank for giving uh, to giving good time for us. Okay, so and a lot of things we are able to know from your presentation. So thank you. And I hope, I think there is no other query, so we can switch to the next session. And thank you, sir, giving your valuable time to us.
Yeah, thank you all. Yeah.
Yes,
Thank
sir. Thank you.
Banibrata.
Hello.